So my talk will be on the concept of Tukey's depth, and my goal will be to give perhaps a rather slow-paced introduction to explain what is Tukey's depth and why it is hopefully useful. And then in the end, I will present the new results that we have obtained in collaboration with a postdoc, Yinan Shen, who works with me, who is also at USC. So if you like the talk, but you want to hear a better version, then please invite Yinan to your seminars. My work in general and the main motivation for this talk is robust statistics. And as we all know, in one way or another, the main goal of robust statistics is to understand behavior of algorithms that have some property of stability under various perturbations. And when translated into real life, this usually results in the presence of outliers. We deal with data that have outliers of one sort or the other. And in math, when we try to analyze such algorithms from the mathematical point of view, we would like ideally to have methods that work under minimal assumptions. For example, we do not want to make any assumptions on the nature of outliers. And I will explain later what it means. This is so-called framework of adversarial contamination. Okay, so before we talk about robust methods, as we always like to do in math, let's start with the basics. Who knows this reference to the spherical horse in vacuum? Okay, so the story is about a sports betting company that hired a team of mathematicians to find the parameters of the best parameters for the racing horse. And after a year of work, they asked them, so how's the progress? To which mathematicians responded, well, we have fully investigated the case of a spherical horse in vacuum. So this is my version of the spherical horse in vacuum. Let's talk about the basic question of how we should order the data. And so why do you want to know this? Well, because ordering of the data induces the natural notions of order statistics and ranks that form the basis of many data analysis procedures, in particular robust data analysis procedures. So if I give you data on a line that looks like this, then the classical order statistics correspond to taking the minimum, so this is the first order statistic, and then ordering them all the way to the maximum. So this sort of third observation becomes the fifth order statistic, the maximum, and 1, 2, 3, 4, 5 stand for the ranks of the data. So it works very well when we are in this one-dimensional framework. However, already as early as late 1920s, Harold Hotelling, who was a statistician and an economist, in one of his studies, he realized that sometimes it is more natural to consider a different way to order data. Namely, we should order the data according to how deep it is in the point cloud. So another way that we can, another word that we can use is we can talk about a center outward ordering of the data. So we should find the most central point and order everything away from this most central point. And by the way, I'll just reiterate it again. If you have any questions, then just feel free to interrupt me, and we'll discuss it. So, what is the formal definition of depth, and why the ordering on this picture looks like this? Well, so the depth basically, to compute the depth of a point, we have to take the the left half line that contains this point and the right half line that contains this point, and take the minimum of the measure of these two half lines. Well, if my measure is just a counting measure, so if I'm just counting the number of points on a line, then the depth is basically the measure of this half line is 3/5, right? So 3 points out of 5 are contained in it, and the measure of this line is also 3/5. So the depth of this point is going to be 3/5, while the depth of this point, for example, is going to be 1/5 because the left half line will contain only 1 point, right? But in general, we can define this for any probability measure as the minimum between these two numbers, and then we can naturally order our data according to depth. So the deepest point, in this case, the median, will get rank 1. Then these 2 points will get rank 2, and 2 points on the boundary will get rank 3. Okay. Now, what about the case of a plane, or more general, higher dimensional space? How do we assign ranks in this case? And since there is no canonical ordering, in this case, well, you can try to do something naive. For example, try to order data according to each coordinate, but this is often not it's often not a good idea, at least because it will not be invariant with respect to the choice of coordinates, which I will talk more about later. So we should find some natural way that we can assign ranks while allowing the data to be maybe moved, rotated, while these ranks are preserved. And this is where the name John Tukey appears. You might have heard about Tukey in relation to many problems. He is in the signal processing community. He is known as one of the authors of the fast Fourier transform algorithm. While preparing this talk, I learned from Wikipedia that he is also credited with inventing the word bit, and he is also one of the fathers of modern robust statistics. So in his 1975 paper, which appeared in the proceedings of the 1974 Congress of Mathematicians, the paper that's very interesting read called Mathematics in the Picture of Data, he suggested a way to use the idea of depth to assign ranks to the points in 2 dimensions. So assume that I have in this case, point cloud that consists of 5 points, and I want to understand what is the depth of this point with respect to this point cloud. So what is the Tukey's way of doing it? Well, Tukey said, let's choose some direction. So let me choose some direction that is determined by this black line. And let me project all the points in this direction. So I drew the line through this x. I projected all the points in this direction, and now I will compute the univariate depth as I described it before. So I will count number of points on the left, number of points on the right, take the minimum of those, which in this case is 2/5 of the proportion of points. And now, well, alternatively, I can think about this as follows. I can look at 2 half spaces. I can look at 2 half spaces that are orthogonal to this black line, and I can count the number of points in each of these half spaces and take the smallest number. And then I will repeat it for all possible directions. So now I will choose another direction, which is a green line. Again, I will project all the red squares onto this green line and repeat the process. In this case, what is the depth of this point going to be with respect to the green points? It's going to be 1, right? Because these four points all project on the right. Only a single point is projected on the left of x. So the depth is going to be, in this case, 1/5. And now, so Tukey said, now do this over all possible directions and take the minimum of depths that you get along all these directions. So that's what's written here, right? So we can express it as the infimum over all directions of the measures of half spaces that pass through the given point in this direction. So, okay, seems like a pretty complicated definition. It's even unclear whether we can compute it. So let me show you how. Let me show you maybe another way to think about it that is often more, at least to me, it's more palatable. So here's another geometric definition. Let us consider this arrangement of 5 points. And again, I take another point. I want to understand what is the depth of this cross relative to the circles. And what I will do is I will try removing these circles and trying to understand whether the x is now surrounded by the remaining points. So for instance, what I did here, I removed this point, and then I drew the convex hull. This is what we call the convex hull of the remaining points. And now this x is not in this convex hull, so it means that the depth of this point is 1. So I removed just one point, and now this point is outside. Now if I take this point, then if I remove just one point, I'm not going to achieve this result. No matter which point I remove, this x is going to be inside the convex hull of the remaining points. So I need to remove 2 points in this case. So if I remove 2 points, then this x is again outside of this triangle. So the depth of this point with respect to the point cloud is 2. Okay? Yes? Well, it's the minimal. What is the minimal number of points that you need to remove so that the reference point is outside of the convex hull of the remaining ones? This is the same. This is the maybe more sort of human geometric definition of Tukey depth. Okay, so can we figure out what are this? If I again look at this configuration of points, can I understand what are points with different depths instead of doing it one by one? Of course, I will spend eternity doing this. Let's try to figure out what is the partition of the plane into points of different depths. So it turns out it's relatively easy to do. What I need to do is I need to draw the line through every pair of blue points, and now this internal pentagon is in fact going to consist of points that have maximal depth. In this case, maximal depth is 2/5. So all of these points here will have depth 2/5. All the points in this gray shaded area will have depth 1/5. And all the points outside are going to have depth 0. Right? And as you see, one of the features of this partition is that all the sets are convex. So maybe you will say that just due to the fact that I chose points that are sort of nicely arranged, but in fact, this property holds regardless of the choice of the point cloud. These depth regions that I will show you more pictures later, but the depth regions are always going to be convex, which is nice. So it's, yes?
Why not the kind of simplistic solution where you just compute distances between points and select the smallest one, next one? Why this is not something that is acceptable?
Very, very good question. Well, because what if I apply a linear transformation to my data? So what if I say squeeze it along some direction, stretch it along other direction? Then distances will change, but relative positions of points are not going to change. So basically, I want my ranks to be independent of the chosen system of coordinates. And many ways to do it, so many natural ways to order the data, are not going to give you that. Some popular methods will allow you transformation that preserve distances, so orthogonal transformations, like shifts, rotations. But the advantage of this approach, since it is only based on relative orders, you can also stretch and contract data. Yeah. So and then other more sort of fine. More fine properties specifically related to robust statistics, I will address them in the following slides. Okay, so if I look if I look at this picture, then again this orange region is the set of deepest points, and if I compute the center of mass, or the barycenter of this region, which I denote by star, we'll call this point Tukey's median. So it's sort of the deepest point of the data, or rather the barycenter of all deepest points of the data. And this point serves as a natural estimator of location. So it's somehow, we can view it as a summary, the one-point summary of the whole point cloud. From the mathematical statistical point of view, the question that we want to ask is how close will this, what I will call sample Tukey's median, be to the population counterpart? So what does population refer to? Well, assume that these 5 points are sampled from some library of data, right? It's a sample from some population. This population can have its center. If I now compute this Tukey's median based on a subsample of the population, how close is it going to be to that population? Okay, this problem is at the core of many more complex estimation problems and algorithms. So the ability to estimate the mean or the center of the population, depending on the context.
Sorry, the Tukey's median, are you referring to the region, the convex region in the
middle? I'm referring to the median itself.
Are you referring to like a single point?
Yeah, I'm just viewing.
Sorry, should they have the same probability? Are you ranking among them? Sorry, I probably misunderstood. I thought like it could be any point in the region that would give you the same value. So
sure, the depth of all points in this region is the same. But now, if I want to use this approach to say what is sort of the centermost point of my data, then the natural thing is to compute the center of mass of this region, sort of the most central point, if you want, and call it Tukey's median. It is going to be one of the deepest points. But now, if you, for example, if you have, say, data from the Gaussian distribution, then this can serve as a natural estimator of the center, so the mean of the Gauss distribution. In this case, I need just 1 point, right? I'm not happy with the whole region. I just say I want to compress the whole sample into 1 point. So which point is the best representation of my sample? Then this Tukey's median could be a viable candidate. Yes?
What happens if you compute the median, basically add all coordinates? Will it coincide with this or not?
No. If you compute the median of each coordinate separately, again, you will run into the problem that it will not be invariant with respect to the choice of basis. You choose 2 different bases, you will get different medians.
Wait. So you consider these points as vectors.
Right.
You add them up, divide by their number. You will get some point in the middle.
Yeah. So just the mean.
Just the mean.
Just the mean, yes.
And it's not coinciding with this.
No. In fact, one of the reasons we want to consider this is because it has a fundamental advantage over the mean, namely robustness. I move one of these points to infinity, the mean is going to follow it, but the median is not. The median is going to remain in this region.
I see.
And it is not just going to remain in this region, but it's going to remain in this region in a very special way that I will explain later.
Okay.
I have one question.
Yeah.
So this median is simply just the mean of these zero, right?
The median is defined as basically the mean of this orange region, yes.
But I mean, in the beginning, the fact that we kind of want to do this approach because the mean is kind of not robust against some outliers, would it be a problem then?
No, because you already, this region itself is going to be quite robust because depth is robust. So depth depends only on the ordering of points, not on the magnitudes, right? So changing magnitudes of the few points is not going to change the depth significantly. So this region is not going to move significantly. Yeah, but okay. Now This is a picture of a more realistic example, and I think here computed it based on something like 50 points. So this is how the depth regions look. So the lighter, in this case, lighter regions correspond to higher depths, and darker regions correspond to lower depths. And what you see on this picture, and so the circle here denotes Tukey's median, and the cross denotes the mean. Right? This is just a sample from bivariate normal population where everything is perfect. So we expect that both the mean and the median will point to the center of this point cloud. But you notice that these contours of these regions are convex polytopes, which is, as I said before, this is a nice desirable property. And what we can expect when the number of points in our sample becomes very large. So this is the plot with 500 points. We see that the depth regions approach, they approach circles, right? And the innermost region, so we expect that the innermost region should somehow approximate the true mean, right? The true center of my distribution. And it turns out that up until this point, the seemingly basic question, namely how big is the most central region, as I let the number of points in my sample grow. So what happens if this set of all deepest points, what I call the median set, how quickly is it going to contract? So this question was not answered, and that's something that I will talk about in more detail in the second part of this talk. Okay. You might have used Tukey's median in some of your exploratory data analysis if you've ever called the backplot function in any statistical package. In fact, so the backplot that produces something like this is based on the notion of Tukey's median. So it computes this innermost region corresponds to the to the half of the data, 50% of the data of highest depth. So this has been used obviously for many years, and is a quite useful feature in exploratory data analysis. It turns out that Tukey depth is known not only in mathematics, but it was, if you want, rediscovered in econometrics. But that's I don't know, maybe Jacob knows this paper. Maybe. So I was hoping that in sociology it might be known, but okay. So it turns out that we can connect Tukey's median to the theory of voting and social choice. So econometricians, well, it's like asking the question is how should we vote, right? So you wouldn't expect that this is somehow connected to Tukey's median, but let me convince you that a very natural model actually leads to the same construction. So I assume that there are several proposals. Maybe there are infinitely many proposals, each of which is encoded by some d-dimensional vector. So each coordinate of this vector describes a certain proposition, sort of d questions, and assume that there are n individuals. Each of these individuals has a top choice. So each of these individuals has one top choice, one top proposal for which they want to vote. And also assume that these individuals are not too polarized, meaning that they rank all the other proposals just based on the overall closeness of the proposal to their top choice. So if a certain proposition X is closer to their top choice than Y, then they would prefer X over Y. So they're not single issue voters, say, right? Not just interested in one specific issue, but this is more mild framework. And we can then look at this function m of xy, which simply tells us what is the fraction of individuals that prefer proposal y over proposal or this proposal x. And then we can define the total opposition to proposal X as the maximal opposition over all individual proposals Y. So what is, so namely, so we're looking for some proposal Y so that it has largest opposition among the voters. And in this framework, econometricians has considered what is known as the min-max majority vote, which is simply the proposition that has the smallest opposition. So let us find the proposition so that the maximal opposition to this proposition is as low as possible. So if you think about it for a while, then it might seem like not such a bad idea, right? Which of the proposals has the smallest opposition? And it turns out that in this society with these voting rules, this theta star is going to be exactly Tukey's median of the top choices of the individuals. And an important property that you might want to have if you indeed were to use this for voting is that you probably want to avoid the situation when some political technologist comes in and tries to suggest some sneaky idea of how to change the way that the different proposals are ordered, and what is the first issue, what is the second issue, and how to represent them so that the vote will be somehow affected. So this is why this property, the property of affine equivariance of Tukey's median, becomes very important. This is the property that I have already mentioned before. So basically, affine equivariance means that the depth does not depend on how we choose the basis to represent our data. In particular, in the previous question, it doesn't matter in which basis I represent or how I choose to represent each proposition. So I can squeeze them, contract them, rotate them. The depth remains invariant. So namely, you can think about it like that. If I have data that live on a circle, and then I somehow squeeze the circle into the ellipse, then the depth of if this point gets mapped to this point, then the depth of this point doesn't change, no matter what I do. Okay, so that's a very nice property of statistical procedures, affine equivariance. Usually doesn't come for free, so there is a price, we have to pay for it. But that's one of the reasons that people like Tukey's depth. Okay, so now let me explain the statistical, more mathematical viewpoint, and what are the kinds of questions that we want to answer in relation. Yes?
Just before you get into that, I was just, it's kind of like back a few slides, but just with the bag plot, just because for, say, those of us who maybe have never used one, can you give an example of like sort of what a question in a data set would be, for which that would be particularly informative?
So it is useful to understand if you do exploratory data analysis, then you want to understand what is kind of the bulk of data looks like. So this innermost region will always contain 50% of data with 50% of deepest points in your data, show you the region, not only the data, but will show you the region that contains 50% of deepest points. Now, this outer region, so the lighter region, is the inner region that is inflated by the factor of 3. So roughly think about the rule of 3 sigma in statistics. Right, that if you compute the mean and the standard deviation, and you take everything that differs by, say, 3 standard deviations from the mean, right, then this gives you, what's it, like 99% confidence interval, right? And then everything outside of this region could be treated as outliers.
Okay, and so using this is just better because it has like more, it allows for more dimensions in the data. Like you're not just looking at like the top and bottom tile or whatever, because it's like considering the geometry, the 50% within multiple dimensions.
Right. So you won't be able to plot it easily in higher dimensions, but yes, typically, as far as I know, statistical packages include 2- and 3-dimensional backplots. It can be defined in any dimension. Yes. Again, the advantage of this is that it can suggest which points can be naturally considered as outliers. That's of course not so far rigorously defined notion, but allows you to see what typical points look like versus outliers. Okay, so now let me focus in the second half of the talk. I will focus on the questions that we posed and partially answered, and I will also try to explain what are the remaining open problems that I'm personally interested in, and if any of you become interested, I will be happy to talk, of course, in more detail during our time at this workshop. So let me assume that my data are d-dimensional and that it is sampled from the normal population. The fact that I'm assuming normal population is not really necessary, so we need to make some assumptions on the data, but I'm just assuming this for the sake of this talk. And the question, again, the fundamental question in statistics, well, can we estimate the mean of this population, the mean mu? And so now let me explain what role is played by the covariance matrix of the data. Right, so the covariance matrix, in some sense, encodes second-order information. It encodes some geometry of the data, and it turns out that important quantity to understand this is the so-called effective rank. So to compute the effective rank, I need to compute the effective rank. I need to take the sum of all eigenvalues of this matrix and divide by the maximal eigenvalue. And what this effective rank really tells me, well, if this effective rank is very small, it basically tells me that my data will look like this. So if the data are, say, d-dimensional but lives close to a smaller dimensional space, then the effective rank will somehow tell me this intrinsic dimensional characteristic of my data. Right? So it's trace divided by norm, yes. Yes, exactly. So in this case, my effective rank will be close to 1. The data are two-dimensional, but the effective rank is close to 1 because data live close to this line. So it turns out that in this case, we can prove the following deviation inequality for the sample mean. So what this tells us is that if I compute the sample mean of my Gaussian data, then the error that I encounter in this case will be controlled by two quantities. So the first quantity is this effective rank divided by the sample size, and the second quantity is somehow the width of the band around this number. And okay, the key feature of this result is that the probability that the sample mean will fall outside of this band is very small, so it is exponentially small. And if you want this probability to be, say, 0.01, then t has to be something like log of 100, so pretty small. And so I try to show it graphically, which is perhaps not my best attempt, but basically what this bound says is that the sample mean of Gaussian data, whose covariance, whose geometry looks like this, the sample mean will basically live in one of these gray shaded regions. It is, I understand, it may be a little bit cryptic picture, but that's what it's going to look like. Okay, so it is not going to live. It is not going to live on the edges. It's not going to live here or here or here or here. But somehow, especially in high dimensions, it will mostly fall in this intermediate region, and the distance of this intermediate region to the mean is controlled by this effective rank. So this is a nice property because it doesn't involve the dimension of the ambient space in any way, and this follows from the celebrated Borel-Ibragimov Gaussian concentration inequality. Okay, now let's consider the framework of robust statistics that we started with. So let's come back to it. And now let us assume that instead of clean data that we denote at x1, xn, the data from the normal population, we observe a different sample that I call y1, yn, where I know that for epsilon fraction of the data, y's are not equal to x's. So think about this as there is some intermediary, some adversary that gets the sample first and then tweaks the data a little bit with possibly some evil intentions, and then gives this tweaked, modified data to the statistician. We know that a small fraction has been corrupted, but we do not know which of the observations have been corrupted. So how can we then estimate the mean of the population in this case? So what would be the good estimator, and what should we expect? So if I plot this graphically, if again I take a sample of about 100 points from the bivariate normal distribution and I corrupt about 10% of them, then I can make the mean to be as far as possible from the true center. So I can even make it go to infinity. So here I just drew it on the edge. But it turns out that Tukey's median is still going to be where we expect it to be. So the Tukey's median was not impressed by such an operation. How can we quantify this? Well, in a paper in 2015, Mengji Chen, Chao Gao, and their co-author Zhenji Ren, I apologize if I misremember this, proved that the Tukey's median that is computed now from this corrupted sample satisfies the following inequality that is very similar to the inequality that I presented before, besides two features. So let me first focus on the positive, or the nice feature. So the nice feature is that the fraction of contamination epsilon comes into this bound in a very benign way. So namely, this bound tells me that the price I have to pay for this contamination is just the small additive factor here, and this epsilon gets multiplied by the largest eigenvalue of my matrix, which is the measure of scale of my problem. In particular, there is no dimensional dependence in this bound, in this factor here. There is no dimensional dependence, and this is in stark contrast with many more natural and simple procedures that you can think about. For instance, if you compute pointwise median, or if you compute what is known as the spatial median, that is the point that minimizes the sum of distances to it, then they're not going to have this feature. In fact, it is very difficult to come up with an estimator that has this feature, and while people have done it in theoretical computer science and in mathematical statistics, arguably none of these constructions is as nice and elegant as Tukey's median. So this property is very special, that it has this correct dependence on the proportion of contamination. On the other side, the negative part is that now the ambient dimension, the dimension of the space D, comes into play. Before it was the effective rank, so sample mean somehow respects the geometry, the intrinsic geometry of the data, while for Tukey's median it was not clear. And so there are reasons why this might be not obvious. So should we expect that Tukey's median will also respect the geometry of the data, or should we not expect it? And well, for once, Tukey's depth, due to its invariance, it does not respect the geometry of the data, because I can move, shift my data without changing the depth, so that if I talk about approximating the depth itself, then the error will necessarily depend on the dimension of the ambient space. Right?
It's a very mild dependence.
It is a very mild dependence, but if D is very large, right? If you're looking at the data that lives in, say, 5-dimensional or close to 5-dimensional subspace of 100-dimensional space, then you're losing orders of magnitude.
Well, but N then saves you.
Sure. In some cases it is mild, in other cases it might be.
Right. But if you control number of points,
right,
you can always minimize the impact.
Oh, so you're absolutely right, but it's a question of our understanding. Can we say for sure whether there should be dependence on D on the effective rank? So it becomes a purely mathematical question, right? We can maybe partially forget about the practical motivation.
So in this formula, T is something that you choose, right?
T is something that you choose. So think about T as the coverage of confidence interval, for example, right? So all these bounds, so they're called sub-Gaussian. Again, this is sub-Gaussian bound because the probability of the estimator being too far is very small. It is exponentially small with respect to this parameter T. As I said, if we talk about the Gaussian sample mean, then of course if we take the average of Gaussians, we still get a Gaussian. So there are no surprises there. But Tukey's median, surprisingly, is even not asymptotically normal. So if say we know from the classical central limit theorem that say the sample mean will be asymptotically normal even in high dimensions, but Tukey's median is not asymptotically normal. Its asymptotic distribution is some very complicated function of the Brownian bridge. So it is not immediately obvious what should be here. And so this is our first result. So what we proved is that if we are in the perfect setup where there is no contamination, then indeed, in fact, Tukey's median satisfies this correct dependence with the effective rank that controls the intrinsic geometry of the data instead of the dimension. Again, this assumes no contamination. So then our next natural question is, well, so what if epsilon is bigger than 0? So we were able to understand this bound, and it turns out that what we thought would be maybe a one-day exercise turned out, for us at least, to be a more difficult question. So for the reason that I'm happy to explain offline. So what can we say if epsilon is bigger than 0? Well, what we can say from the known results that if epsilon is large, if epsilon is bigger than something like square root of d over n, that's what I mean by large, then, of course, this factor square root of d over n becomes non-important because it is simply dominated by epsilon. So in this case, we know that the previous known bounds already gives us correct dependence. So the only interesting case is when epsilon itself is smaller than this term. Then the question becomes, if I introduce outliers, do I break this respect of Tukey's median for the geometry of the data? Does it suddenly become dependent on the ambient dimension instead of the intrinsic dimension? Okay, so what we're able to show is that if the proportion of contamination is very small, so smaller in order than n to the power minus 1/2, then this doesn't happen. Then Tukey's median still behaves as it should. And in this case, of course, this factor epsilon n, it simply gets subsumed into the bound. So basically, in this case, Tukey's median behaves as if there is no contamination at all. So you corrupt a small number of points any way you want. The Tukey's median doesn't care. So it maintains all of its optimality properties. But there are, of course, certain caveats. So there are a few caveats. So the first question that I really want to understand is what happens in this critical regime when the fraction of contamination is of the same order as this leading term in this bound. And it turns out that our methods are completely useless and blind in this case. So there is something new that we don't know. Something new is needed to understand this result. And second, if the effective rank and the ambient dimension can grow with the sample size, or we consider this type of framework. And in this case, it is also absolutely not clear what is going to happen because the small o of one term, it hides dependence in these two quantities. So if I let them grow with n, then this might not be small o of 1 anymore. So something that we also don't understand. Let me say a couple of words about how one can can try to prove this result. It turns out that to understand the error of Tukey's median in this adversarial contamination framework, what we need is we need to understand the diameter of the set of deep points. So if I look at this picture now, this region marked with a red curve shows me the deepest points of my sample, and this blue region are not the deepest point, but say the points with depth, the difference at most by epsilon from the depth of Tukey's median. Now what can happen when I contaminate, or when I introduce epsilon contamination to my data? So I change at most epsilon fraction of points. Well, I can change depth at most by epsilon, right? Since, again, depth only depends on the ordering of the data, I can move epsilon fraction of points from left to right. I can change depth at most by epsilon. And therefore, this implies that the median that we obtain after epsilon contamination must be somewhere in this blue region. It cannot escape this blue region, right? And therefore, to understand how far this median is from my population mean, I need to understand the diameter of the set. I need to understand how big the set is, right? For value of epsilon, that is very small. So in particular, if we're able to answer this question, we're also able to say, well, what is the size of the set of all deepest points, right? And I will state one corollary of the theorem, is that the corollary is one of the questions that originally motivated our work, is that we consider the set of deepest points, then its diameter goes to 0 faster than 1 over square root of n. So I wrote it this way, that square root of n times the diameter of the set. The set itself is random, depends on the data, so it converges to 0 in probability. And graphically, what it means is that the picture that we are looking at, it looks like this. We have our population mean. We have the Tukey's median, the centroid of the set of all deepest points. And this distance is somewhere on the order of 1 over square root of n. But the set of deepest points itself is very small. It's a small set around Tukey's median. And its diameter is much smaller than this distance. In particular, the population mean mu is almost never in the set of deepest points. It is never going to, its depth could be very large, but it is never the deepest point, which is perhaps a curious remark to make. OK, and what are the other open questions? This question that I thought that we will be able to answer when we started this project, but we haven't answered it exactly, is what is, say, in the case d equal to 2. If my data are two-dimensional, what is the exact typical size of the diameter of the set? What I mean by the exact typical size, well, maybe it's something like n to the power minus 3/4. So here I can only say that it is smaller than n to the power minus 1/2, but can we say more? We should be able to say what it is exactly. Another question that might have practical applications is whether we can extend this framework that considers essentially one center of the data, can we extend it to the k-means framework, which would apply if our population is given by the mixture of several nice distributions, for example, a mixture of k-Gaussian distributions. Right? Can we then somehow use the notion of depth to try to estimate the k-centers of the components of this mixture? Okay. So again, I will be happy to discuss any of these problems if you feel inspired. And with that, let me thank you for your attention. I'm happy to answer any remaining questions.